Okay, we will start looking at some applications for Schrödinger equation. And the first application that we will look at is a very important problem, which is the potential barrier problem. And let me start by describing the problem. And here we imagine that we have a beam of particles. This beam of particles that I show as a blue arrow here, each particle has an energy E which is larger than some value or an energy barrier U naught. Apparently, this energy barrier is a barrier that exists at x equals 0. So this is a one-dimensional problem along the x-axis, and we have particles, each particle of energy E incident on a barrier, an energy barrier, which is of height U naught. And apparently the energy E of each particle is higher than the barrier height. So that's what we have here. Okay, so what we expect from classical mechanics is that since each particle has an energy E which is larger than U naught, then from classical mechanics we expect that all particles will make it through the energy barrier and therefore will be transmitted to the right hand side, okay, at x larger than 0. As we show here, a yellow transmitted beam. So classically, all the electrons with energies E larger than U naught, which is apparently all the particles in the beam, would be making it through to the right hand side. No particle is expected to be reflected, as we see here in the green arrow. That is classically. Okay, now we said particles in quantum mechanics can be described by waves. So the incident particles are described by this blue wave here, which is a large wave, meaning that we have a large density of particles. And then the yellow wave on the right hand side means that all the particles were transmitted through the barrier, and so we still have a wave on the right hand side. Classically, we shouldn't have any reflected particles. So this green wave should not exist classically. All the particles should make it through. Okay? So that should be the picture. The analogy here is if you think of yourself as a particle and then you come walking and have some energy and then you suddenly find a stairway or few stairs to climb to get into a higher region. If you have enough energy to climb these stairs, then you can climb them and then you can go to the higher region on the right hand side. Okay? So there is nothing to stop you from climbing the stairs, nothing to reflect you, if you like, from going through to the right hand side region. That is classical. However, we will see unexpectedly that quantum mechanics predicts that some of the particles are reflected. So there is non-zero probability, that is, some of these particles will be reflected even though they don't have, they have enough energy to surmount or to go above the barrier at x equals 0. Okay, so this is the main thing. Okay, so and let us go through Schrödinger equation and see how can we possibly have some of these particles reflected. Okay, now we know that Schrödinger equation from earlier on has the potential, okay, potential U. So let me just go back and tell you that U is equal to 0 in this region. There is no potential here. The potential is 0. And U is equal to U naught in this right-hand side region. So this is a potential step, if you like. So the potential is a U0 here in this side, and the U equals U naught. So when we use Schrödinger equation, which is when we use the position dependent Schrödinger equation, we should use the right potential energy. Okay, so let's assume, and we know from our previous lectures that we can write the wave function capital Psi as two functions: a position dependent function psi of x and a time dependent function phi of t. That is the method of separation of variables. That is how we can do it. Now, phi of t, we know that it goes like E minus I omega t, where omega is the energy E over h bar, right? So that's what we have. And if psi of x, we thought it varies as E I k x, where k is what we said is the wave number. So the two together, psi x phi of t, would have this exponential dependence, eik1x minus omega t. Now, this I here stands for the incident wave. So here we are looking at this wave here. So this wave is psi I, the incident wave, or more clearly here, this is our psi I, the incident wave. And our wave number here is K1, okay? So in that case, what we have is AI, that's the amplitude for the incident wave, AI, eik1x minus omega t. Omega is the frequency, the energy of the particles. Remember also, since the energy is E, then omega is the total energy of the particles, E over h bar. Okay? Total energy of the particle. Okay? E. So this is the incident wave, and it is in the region x less than 0. That's the left-hand side region. Now, let's assume, we know classically that doesn't happen, but let's assume that there is a reflected wave. So again, the reflected wave is this wave here. And I'm going to call it psi r, r for reflected. Okay? Or it is this green wave here, psi r, where r is the reflected wave. Okay? Now again, in this region, my wave number is K1, right? So again, this wave, if psi r, will have the same wave number K1, okay? It will have a different amplitude. As you can see, the total number of the particles incident is so large. So the amplitude AI must be larger than the amplitude A sub r for the reflected wave. So this here is the reflected wave, okay? And again, it will happen in the left-hand side of the barrier. And R for reflected, and A sub R is the amplitude of the reflected wave. Now again, I'm using the same wave number K1 on the left-hand region, but look at this minus sign here. And the minus sign indicates that the wave propagation is in an opposite side to the wave propagation of the incident wave. So the reflected wave actually moves from right to left. The incident wave moves from left to right. So that is why we get a minus sign here. The energy is again represented by omega. Remember, omega is E over h bar. Again, on the left-hand side, the energy is E for the particles. Okay? So this is the reflected wave. Now, in the region x less than 0, that's the left-hand side region, we have two waves, incident wave and reflected wave. So the total wave on the left-hand side, okay, which is this wave here, would be the sum of these two waves. And the sum of these two waves gives me the resultant wave on the left-hand side, which describes all the particles on the left-hand side, which are the incident particles as well as the reflected particles. So my wave on the left-hand side, my wave function on the left-hand side meaning x less than 0, is equal to the incident wave psi I and the reflected wave capital psi r. Okay, so this is the wave on the left-hand side here. Now, let's go to the right-hand side. And the right-hand side here, we have this yellow wave, which is the transmitted wave. Now, on this side, we will have a different wave number, maybe calling it K2, right? So, in this left-hand side, again, the propagation is from left to right. So, my transmitted wave, or the wave on the right-hand side, x larger than 0, which is t for transmitted wave, is equal to a sub t, which is the amplitude. And now I'm using K2, a wave number on the left-hand side, minus omega t. So now I'm going to use Schrödinger equation. Now, my Schrödinger equation, remember, it is minus h bar squared by 2m, and then nabla psi squared over nabla x squared plus e minus u naught minus u times psi equals 0. Okay? So, in fact, this is plus here, because since I have, since I have everything on left-hand side, it is plus. So, now, on the left-hand side, here, u is equal to 0. I don't have any potential. The potential is 0. On the right hand side, U is equal to U naught. So this equation takes the form minus h bar squared over 2m delta squared epsilon bar over delta x squared plus E. U is 0, okay, on the left hand side. And on the right hand side, U is equal to U naught. So what I'm going to do is I'm going to take these two functions, substitute them here, and then apply these functions in this equation, right? Taking x equal to 0 and see what I get. And if I do that, I get this equation here. So when I substitute for the left-hand side, you get h bar squared, k1 squared over 2m equals h1, h bar omega. Similarly, when we go to this x larger than 0, substitute this function into this equation here, which is Schrodinger equation, but now use U naught instead of 0, because on the right hand side we have a U naught potential. And if you substitute, then you get this equation here. So in summary, what I'm doing here is I'm assuming two solutions. One solution for the right hand side here, and using these two functions here and here, and then one solution for the right hand side, okay, with this function. So a left hand side solution for x less than 0 and a right hand side solution for x larger than 0, substituted in the Schrodinger equation for U equals 0 on the left hand side and for U equals U naught on the right hand side. And once I substitute these solutions, I find out that the conditions, the two conditions for these solutions are these. Okay, so these are the conditions, and these tell me that the total energy of the particles, K1, is the wave number of the particle on the left-hand side region. Okay, since I don't have any potential energy, then the total energy, h bar omega, this is the total energy. All of it is kinetic energy. Remember, this is all kinetic energy because h bar squared, k1 squared, it's like the momentum squared. This is simply p squared over 2m. And p squared over 2m is all kinetic energy. No potential, zero potential. What I'm having here is I have another wave number k2, okay? And so here I have the kinetic energy, but on the right-hand side I have a potential energy U naught, and this is my total energy E. So now my total energy for each particle on the right-hand side has two components, a kinetic energy and a potential energy U naught. Okay, so this is one condition, you know, that we should have satisfied for these solutions. Now, another condition is the following. In order that epsilon star or complex conjugate epsilon can have physical meaning, epsilon and its derivatives must be continuous. So to have meaningful probability distribution, which is this, I have to have a continuous psi and a continuous derivative of psi with respect to x. So a continuous psi, if you look here, I have two regions. I have region x less than 0, and I have region x larger than 0. Now, this point here, x equals 0, is a point of break, between the two regions. So, to have a meaningful wave function, this wave function and its derivative should be continuous at x equals 0, meaning the value of the left-hand side wave function at x equals 0 should be equal to the value of the right-hand side wave function at x equals 0, so that we get continuity at this point. The two values of the wave function at this point should be the same. This is exactly what is written here. This is our wave function on the left-hand side for x less than 0. Okay, this should be equal to our wave function on the right-hand side for x larger than 0, everything at x equals 0. So what I should do, I should go back, okay, to these two. Okay, maybe clean this up a little bit. Okay, maybe clean it up a little bit, and maybe now use this wave function here and this wave function here, and then evaluate these wave functions at x equals 0. Okay, and then also evaluate this wave function at x equals 0. So if you use x equals 0, this becomes 0. If you use x equals 0, each one of these becomes 0. This one also becomes 0. Okay? And then you have e minus I omega t. Here also you have minus I omega t. Here also you have minus I omega t. So you can actually cancel e minus I omega t throughout. And so what you get is ai plus ar equals at. So that would be the condition. Okay, so that's exactly what we have here. AI plus AR equals AT. So this comes from this. Similarly, now you require that the derivative of psi at x equals 0 is continuous. So this is psi at x less than 0, and these are the derivatives. And then you evaluate the derivatives at x equals 0. And then you set it equal to the derivative of psi, the transmitted psi, at x equals 0. And then I leave you to do that. Just take the derivatives again, go back here, take the derivative delta psi I by delta x, and for the derivative, you get I k1, and then the same ai exponential I k1 x minus omega t. That's what you get for the derivative. And then you evaluate this derivative at x equals 0. And evaluate this derivative at x equals 0, what you get is I k1 ai. And then you get e minus I omega t. And then you do the same to this one, and you evaluate it at x equals 0. And again, you get I k1, but then ar e minus I omega t. And then you do it here also for this one. And then you evaluate it at x equals 0. And what you get is I k2. Now here you get minus sign, right? Because here you have minus, right? Minus sign. So ik2, and then you get A transmitted, again, times the exponential factor. Okay? So if you, again, do these and substitute here, what you get is this relation here. So you get some relationships between the amplitudes of the incident, reflected, and transmitted waves. And then you solve all of these. You get the reflected wave amplitude in terms of the incident wave amplitude, and the transmitted wave amplitude in terms of the incident wave amplitude. So then the amplitudes corresponds to the intensity of the waves, correspond to the number of particles, if you like. So if you do that, then we immediately get that the reflection coefficient R, or the coefficient of reflection R, is equal to the amplitude AR squared, the reflected, and over the transmitted. And then you get it equal to K1 minus K2 squared over K1 plus K2 squared. Similarly, the transmission coefficient, that is the ratio of those transmitted, depends on the square of the transmitted amplitude and the square of the incident amplitude, and you get this ratio. So remember, we started off by saying E is larger than U naught. Okay, so the energy of the incident particles is larger than the barrier. However, we still find some of the particles reflected. So this is a very important relation, or a very important conclusion. It is not the same as what classical mechanics would tell us. What we're finding here is that even though the energy of the particle is larger than the barrier, not all of these particles are able to be transmitted through the barrier, go to the other side. Some of them are reflected. Even though very little number is reflected, most of them are transmitted, but the fact that we have few reflected is counterintuitive. It's not like what we expect from classical mechanics. Okay? So let us just let us just look at another scenario. Let me go back, all the way back to this drawing here, or this sketch here, and let me clean things, right? And now let's say that we take a situation, or we take a condition such that E is less than U naught. So what we are saying here is that the energy of the incident particles is less than the barrier. So in this case, we're saying that the barrier is so high. Okay, so the barrier U naught is big. Okay, classically, using classical mechanics or Newton mechanics, what do we expect? All the particles have energies smaller than the barrier. So they should all be reflected. Nothing should go through the barrier. So all of this blue wave should be a reflected wave. No yellow wave, no transmitted wave. However, quantum mechanics tells us that we still find some of the waves transmitted, even though the energy is less than the barrier. Now, that's surprising. Okay? Now, how does that change the calculations? Or how does that change the solutions? So, I'm going to do the same thing. Assume an incident wave with wave number k1 in the left-hand side region and with frequency omega. Then assume a reflected wave, psi r, again k1, wave number, and omega frequency. And so the total wave on the left-hand side is x less than 0. It's a sum of the incident wave and the reflected wave. The transmitted wave on the right-hand side is ik2x minus omega t and an amplitude t. Now, from classical mechanics, I expect this to be 0, no transmitted wave, because E is less than U naught. But as I told you, we will find that there is a number of particles that are able to make it through the barrier. Okay? Again, let me clean